Уже началось, что ты, может, включишься? Okay, let's start now. Hello, everybody. It is a pleasure for me to announce the talk by Professor Shun Pei Miao. She will tell us about gauge-independent effective field equations. Please, 1 hour.
Okay. Thanks very much for introducing me and giving me this opportunity to speak in this seminar. It's my pleasure. This work actually is in collaboration with Thomas Lopez. Do you hear echoes? Sorry, do you hear a lot of echoes?
Now it's okay.
No, it's okay. Okay.
Yeah.
So the work actually is mostly based on the archive paper. This one. I mean, so if this is the first slide. Before I go to the main part of my talk, I would like to talk about some misconception about quantum gravity. Suppose right now we have a quantum gravity corrections to electromagnetism. Now, actually, I'm teaching graduate classical electrodynamics, and we all use, we can solve the Maxwell equation for local fields at finite space time points. No hand wringing about the physical interpretation. We always can talk about, for example, the single charge particles or the current density, how they respond to the external electric field or magnetic field or both. It's no problem to interpret the result we obtained from Maxwell equations. However, we have been told as soon as quantum gravity is non-zero, no matter how small it is, we only can study it at the context of asymptotic scattering theory. And we also have been told we no longer can study the local fields at finite space-time. And also, for example, the causality problems, such as how the source responded to the field is outside or inside the light cone, such causality problems, we only can study it through these analytical structures of S matrix. For example, this like the cast or poles in the momentum space of S matrix. So it seems very, very weird when you turn from zero quantum correction, quantum gravity correction to non-zero quantum gravity correction, then you have to use entirely different method to study it. And of course, you say it's because S matrix is gauge independent. However, this kind of stuff actually doesn't make sense sometimes. For example, we measure things at finite time and at finite space, okay? So S matrix doesn't really correspond to what we measure stuff. And also, this asymptotic scattering theory cannot be extended to cosmology. For example, during the inflation, we know for talking about the scattering theory, we know we need to send out the source into this infinity early times and static early times, and also and static future times, and all empty space, empty states, freed of quanta, freed of particles. However, during the inflation, we don't know what is in vacuum and out vacuum. In vacuum could be the sort of like initial singularity, and the out vacuum could be full of these inflationary gravitons. So we don't know, and we also do not have well-defined S matrix during the inflation, also in cosmology. And even if S matrix exists, it also is not observable because we cannot measure, we are not able to measure entirely final state at asymptotic future times. You can think of the two observers initially apart about 1 Hubble distance. Because rapid space-time expansion, very quickly these two observers will lose the causal contact. Even the light cannot communicate with each other. So it's not possible to collect all the final scattering results. So even if S matrix exists on this theta, or we said during the inflation, it's not observable. We cannot really do that. Okay, so I will say we should just study quantum gravity in not using the S matrix. This is the flat space-time sense of S matrix, even though this is gauge independence. So if we come back to study this quantum gravity effects using this effective field equation, like the way we solve this graduate classical electrodynamics, we solve this Maxwell equation. It doesn't mean this gravity loop correction poses no problem if you use this effective field equation. For example, this is a quantum corrected Maxwell equations with vacuum polarization. This pi mu nu is vacuum polarization. You can see the first term here actually is just a classical term, and the second one is from the quantum correction one. J, of course, you know this is a source. Okay, in order to use this Maxwell equation, the quantum correct the field, we need to compute vacuum polarization. And in order to compute the vacuum polarization, we also need a graviton propagator. So let's pick up the simplest background. Let's flat space background. And this matrix is like you have eta mu nu plus some fluctuation kappa times h mu nu. And we add these average gauge conditions to Lagrangian density. And this is the F mu takes this form here. Alpha, beta are arbitrary gauge parameters. So if you compute this vacuum polarization at one loop order using dimension regulation, you can see most of this quantity. For example, the quantity inside the parentheses actually is fixed. 1 over delta x to 2d minus 2 also fixed. Eta mu nu partial square minus partial mu actually is fixed by this gauge invariant form. And also you can see kappa square here is one loop. It indicates one loop order. So by counting the dimensionality, you will know the some length dependence must go like 1 over length raised to 2d minus 2. And also by Poincare invariance, you know it must form like a delta S square here. So it's a scalar product of length separation. So the form from here, that is from this parenthesis to 1 over delta x 2d minus 2, actually is fixed by gauge invariant dimensionality and also this Poincare invariance. However, you still have something unfixed. This is C naught. C naught is gauge parameter dependent coefficient here. And actually you can, this because alpha beta is very, could be arbitrary. You can see from the form here, if you choose beta equal to 2, for example, it diverges at the second term and the final terms, if you choose beta equal to 2 and alpha equal to 5. So if alpha equal to 5, you will see 5 minus 1 is 4, 12 times 4 is 48. It's the same coefficient for the final term, so it gets canceled. However, if you choose alpha a little bit more than 5, and the beta approaches 2, you will find out the positive infinity win. So this C naught will go to positive infinity. If you choose beta approaches to 2 and alpha a little bit less than 5, you will find out the final term win. So it goes to negative infinity. So C naught is highly gauge dependent. It ranges from minus infinity to positive infinity. So vacuum polarization is highly gauge dependent. And of course, the computation from this effective field equation also highly gauge dependent through this gauge dependent vacuum polarization. So this is indeed a big problem. And you might say, okay, we can write this effective field equation in gauge invariant form. We can represent this vacuum polarization using a structural function. Here, this is structural function. And the term inside the parentheses is gauge invariant form. Okay, by plugging this, and we can rewrite this Maxwell equation, quantum corrected or effective Maxwell equation. So you will see this convert the gauge potential to the field strength. Equation only involved the gauge invariant field strength tensor. So this is U1 gauge invariant. And also probably because this equation already specialized to the background, you might not see it's manifest, but actually it's also general coordinate invariant. For example, the first term here, this is a partial nu acting on the F nu mu. So in some non-trivial background, this term could write like you just insert a square root minus g and also 2 inverse matrix. Okay, so actually the whole term is gauge invariant. It's U1 gauge invariant. It's also general coordinate gauge invariant. Okay, and then you might say, wow, this is gauge invariant. So the result must be okay. However, you can see this structural function. Indeed, under one you can transform on with the fixed alpha beta, and you do the gauge transformation. This structural function still keeps the same form, and we can say, okay, this is gauge invariant quantity. However, it doesn't mean it doesn't mean it doesn't depend on the gauge parameters. So it's still gauge dependent. Okay, and recall C naught. These parameters actually varies from minus infinity to positive infinity. So they make the computation from effective field equation could be arbitrary. It could be anything from minus infinity to positive infinity. And indeed, this is a very big problem in quantum gravity. And so this also occurs in other fields, not just the quantum gravity plus electromagnetism. For example, quantum gravity plus this massive Markov scalar. This is kinetic terms, and this is a scalar propagator equation on phase space time. It has very simple form, and you also can use this. Here is a self-mass square. That is one pi 2-point function. So you also can solve this effective field equation, quantum correct this effective field equation, but you still find out this mass, this self-mass square, carry this gauge parameter dependent coefficient C naught, the same as before. The similar gauge dependence also occur in other theory, for example, in the gravitons, also in the graviton self-energy, also in this fermion self-energy. So people might think, maybe we should have the other approach, for example, Velikovsky approach. In 1984, in this paper, Velikovsky proposed this unique effect action in quantum field theory. The idea is replace integral d4x j dot phi in a generating function of a path integral formalism with the integral d4x j dot invariant length in the field space. So this actually requires the field space metric, and it's not very clear what is the physical principle to pick up this field space metric. Maybe we can obtain it from the action, the directed turn in the action, but there's no very clear indication for this part. People actually use a Villkovsky approach to compute effective action. And he found out this Villkovsky effective action equivalent to the usual effective action in particular gauge, this Landau-DeWitt gauge here. This proof is shown in this paper. So it seems that for the quantum gravity, if you choose using this Villkovsky approach, it just amounts to choosing a particular gauge, choosing a different gauge. And so it seems to me it's just like you replace the old problems that is arbitrary gauge choice with the new problem that is arbitrary field space matrix choice. This is not really improvement, but it's not wrong to use this approach. The problem is using it to have a wrong physical interpretation of this effective potential. We know effective action actually includes all direction in the field space, and effective potential is just the one direction in the field space, and effective potential computed at this constant field configurations. So some people compute effective potential in one gauge for one theory and get stable conclusion. Then he also compute effective potential in another gauge for the same theory, get unstable result. And then they make a wrong conclusion using this Villkovsky approach. This makes him think there exists a preferred gauge, so that will lead to this unique effective action. However, I think the correct interpretation means you have effective potential compute in one gauge and you have unstable result. That just means this theory is unstable. It doesn't mean you have to choose the preferred gauge which make effective potential stable in that gauge. It's not such interpretations. However, you might say, is this bad? Okay, I say this is not entirely bad, because if you compute in one gauge for this effective potential, and that means you compute in the constant field configuration in this gauge. If you do the gauge-dependent transformation to another gauge, that means in another gauge is no longer this constant. Is no longer constant field configurations. So actually, it's in other direction in field space. So actually allowed you to explore more directions in field space. And I will say this is not bad. It actually is good, allow you to explore more directions in the field space and to get more information for the effective action, because we don't have infinitely computing ability to compute the effective action. This is why we pick up the one direction to compute the effective potential. So I will say we should very careful to interpret the result. And so far, we will see.
Can I ask you, sorry. Can I ask a question about what you said? So I'm a bit confused. So in the Villkovsky effective action, it is derived in this covariant perturbation techniques using this heat kernel method, which is around any arbitrary background. So, are you saying that this action is wrong, or
I don't mean Asian is wrong. I just means if you want to solve the gauge independence problem or gauge dependent problem, this probably doesn't improve much, because if you have different field space metric, it just means in the regular sense it's just arbitrary gauge choice, but it doesn't mean it's wrong. It's still open issue. But in my sense, I will say it seems very complicated to use. This is my opinion. Maybe we can discuss this more later.
Okay. Sure.
Okay, so the gauge issue still exists. Okay, and here I would like to make a comment about this gauge dependent stuff. We all know this 1PI 2-point function is gauge dependent, but it actually contributes to the gauge independent S matrix. This is the previous genius find a clever way to separate this gauge independent information or on the 1PI 2-point function to form this gauge independent S matrix. So this means even though 1PI 2-point function is gauge dependent, we should not say, oh, this is garbage, just throw it away, because it must contain gauge independent information, some physical information we want. Otherwise, you cannot glue all different 1PI 2-point function to form S matrix, which is gauge independent. So we just need to find a clever way to separate this gauge independent information from gauge dependent nonsense. Okay, so we don't think this effective field equation, the result so far we get through this 1PI 2-point function is gauge dependent. So we just abandon it entirely at the first place. Okay, and the physical problem seems to be we neglect the quantum QG correlation from the source, which disturbs effective field and observer who measures it, because we know that everything interacts with quantum gravity, and neglecting this interaction is what causes gauge dependence. So here, actually, I would like to model the source and the observer using the S matrix. You might say, okay, a few minutes ago, you just persuade me in cosmology, S matrix is not well defined and even not observable. But right now you say you want to using the S matrix to model the source and observer. Here, I mean, I would like to pick up the intermediate steps of a form S matrix. This procedure, but I don't mean I would like to push this initial state and the final state to the asymptotic early times and the asymptotic future times, just to avoid the situation we mentioned at the beginning slide. And we also like to do this in the position space and the view important part of amplitude's correction to the 1PI 2-point function. And very few by explicit computation, the end we find out very few properties of the source and observer survive. That means the details of a source and observer doesn't make much different, doesn't make the result different at the end. Actually, this makes sense. For example, if the same people collect the data and it doesn't matter, these some people have a blue color eyes or the brown color eyes, right? So the source and the observer details actually is not important here. We actually implement this procedure for matrix minima color scale on flat background. So this is Lagrangian. The script phi is matrix 1, and the per se here is matrix 1. So this is the kinetic term. This is a matrix kinetic term, matrix kinetic term, this mass term, and this is the interaction term lambda phi, script phi per se square. And I delta of x plane is matrix scalar propagator. I delta psi m x plane is matrix scalar propagator. And here is a special part of, alpha equal to 1, beta equal to 1 Grattan propagator takes this form, okay, the simple form. This all on flat background. So right now, I would like to model the source and observer as massive scalar particles and consider scattering by the exchange of these massive particles. So let me show you the diagram. For example, like this one, this is a solid line is massive scalar, dashed line is massive scalar, and wavy line is graviton. Okay, so the unplanned coordinates, this part, this is observer part, and this is source. The planned coordinates here is the source part. So you have incoming observer, incoming source, and outgoing observer, outgoing source. This is all formed by massive scalar. This is scalar, okay? And here I would like to have exchange massive potential. For example, the tree order is just entirely one solid line, okay? So this is what I mean here. And QGH, quantum gravity actually corrects this massive scalar exchange propagate. This is the part we have 1 pi of 2-point function in these diagrams here, okay? This is a graviton, quantum graviton. The graviton loop correction corrects this massive minimum couple scalar propagate. Okay, here, and this is the source, this observer and the source scattering amplitude. This is the part we already have included in the 1 pi 2-point function in the effective field equation. And the part we do not have in the original effective field equation is quantum gravity correction corrects the vertices and also propagation of this scalar, massive scalar propagate. This is missing part. So let's see this diagram here. For example, this diagram. This is quantum gravity correction corrects X, this vertex, observer part, and as planned, source part. And also, you can have this kind of a 3-point amplitudes diagram. This quantum gravity correction, okay, it corrects this outgoing vertex and also corrects this massive propagation, okay? And you also can have this kind of 4-point amplitudes. So this quantum gravity correction corrects this propagation of a scalar, massive scalar, and also this part, okay? So actually, if you include all this quantum gravity correction to the observer and the source, this is not a whole diagram. I only display a few of important diagram. There are, for example, this kind have I think 3 more. This all have 3 more. This have the other counterpart. So you include all this QG correlation from the source and also from the observer. Okay, this is the idea. And of course, you can see from this slide, you have this 2-point, 3-point, and 4-point function diagrams. Okay, something like that. And we would like to consider all, not just this one. And then here I give you one example. This example is, let me just write down. This is 3-point diagram amplitudes in the previous slide. So let me go back here. You can see you have one graviton propagate. This is a massive scalar propagator. And also this is a massive scalar propagator. And you have 3 vertex. Okay, this is per C square-free vertex. And this is 1 graviton, 2 massive per C vertex. And this is 4-point vertex. It's more complicated. And in position space, actually just glue all the vertices and propagate all together. So this is a vertex here. This vertex is here. This is the other vertex, 4-point vertex is here. And the 3 propagator is massive propagator, massive scalar propagator, and this is a graviton propagator. Okay, so you write down the diagram, then you contracting the indices and using the external state and also propagate the equation to simplify these diagrams, and you can reach this form. Bar, you see this the white bar here, that means the derivative acting on the external state. That is, you have a derivative acting on this line, not internal one. And we use the equation of motion for the massive scalar propagator to reduce it, and also use the propagator equation to reach this simpler form. And here come to the crucial step. That is, we have to use the relevant Donahue identity to reduce the form into the form only have a two massive scalar propagator. So you see here you have one massive and two massive scalar propagator. Then you use the Donahue identity to reduce this, and this is very important. Donahue actually he computes these quantum gravity corrections, and he find out there is a certain piece is actually is non-analytical structure. One non-analytical structure actually corresponds to and contributes to this long-range contribution, and the other is semi-classical correction. And we are only interested in this long-range part. So we take his result in momentum space and derive it in the position space. So this is where the identity comes from. And this allows us just to pick up the important part, that is gauge-independent part, for us to form the important, finally gauge-independent, this 1pi two-point function. So in this, after you reduce using the relevant Donahue identity, then you reach this form, okay? So kappa square, lambda square just indicate one loop order, this young coefficient. And here the delta function just set up 4.1, for example, this one set up x equal to y, x prime equal to y prime, and reach this kind of form, okay? Only this propagator and this propagator. So all other diagrams, for example, if you reduce from the 4-point amplitudes diagram, also have this same space-time dependence like this. And the only difference is the coefficient is different here. And this example I give you here is in the particular gauge that is alpha equal to 1, beta equal to 1, because it's simpler to perform and show you. And actually what we have done is arbitrary for the arbitrary alpha and the beta. So actually it can be done for the arbitrary general alpha and the beta, okay? And so how do we interpret this and extract this 2-point amplitudes as correction to the 1pi two-point function? So recall the contribution to this massive scalar scattering from this massless self-mass square. So let's go back to the important diagram, this one. This part without attach this massive propagator, only the central part here is the self-mass square. The mass is the self-mass square of z prime. Then you attach two massive propagator, xz and s prime, z prime. So this is, I rewrite, I just rewrite the diagram, and it has this form. Minus I lambda is just from the vertices here. So then later we use this propagator equation. The propagator equation that is, you have partial square derivative acting on the scalar propagator equal to I times this Dirac delta function. So suppose right now we have generic 2-point amplitudes, which reduce from the 3-point and 4-point amplitudes. One and takes this form, lambda square times function of xs prime. And I would like to rewrite this function as the form like this, the standard form, so that I can compare what is the correction to this self-mass square. So the idea is just insert 1. For example, this is 1 here. You integrate against the Dirac delta function. Here, integrate against the Dirac delta function, right? So this is 1, and minus is just because I want to compensate. I insert 2i here because I want to use this propagator equation by convert I, this Dirac delta function, as two derivative acting on this scalar propagator. And later, we just do integration by part. So all these derivative, because here have this I times Dirac delta function actually is 2 derivative acting on the scalar propagate. Here is also 2 derivative acting on the scalar propagate. Actually, you can convert the derivative from x to z, here from s prime to z prime, because it's just the separation. You will off the sign, but you have a 2 derivative, so minus become positive. And you just slope this derivative to this function f of z prime, so you reach this form. Then you see the blue line here. This blue line at the beginning is identical for the standard form. So actually, then you can make a conclusion that is this part is the correction to this 1pi 2-point function, this guy. So I do this, I mean, you have several different diagrams. This diagram, or this kind of diagrams, you all reduce to the form lambda times function f of xs plan, then rewrite it using the propagator equation and reduce to the form you can compare with this diagram. Then you can refer to what is correction to this 1pi 2-point function. So you can do many diagrams as the same procedure here. I here just indicate different diagrams of coefficient. Here is the result. The left-hand part, this table, is for messages in Markov scale on flat background has this quantum gravity correction. And here I just slightly change the notation, alpha equal to A and beta equal to B. So this is the I equal to 0 is one kind of diagram. I equal to 1 is the other kind of diagram. So you have 6 different kind of diagram, and each diagram have a pure number times some gauge-dependent coefficient times this gauge parameters, and this coefficient times this gauge parameter. It's the form of 1 over beta minus 2, and also coefficient times this kind of gauge dependence parameter. So if you add, you look at the second column, third column, the fourth column, you add all this gauge-dependent coefficient altogether, it winds up to 0, 0, 0. So indeed, this procedure successfully eliminates all the gauge parameter dependence here, only left the pure number. And the right-hand side is the work done by the graduate student at UF, Kutawa, and also Professor Uda. So this is the quantum gravity correction to EM. And here they only did it in linear order of alpha beta because the propagator become complicated. So only in the linear order. Delta alpha here is just alpha minus 1. So OI is pure number, AI is coefficient of linear order of alpha, BI is coefficient of linear order of beta, is gauge parameters. So it's the same, you will see all these gauge dependence wind up in this coefficient add up equal to 0. So indeed, at least the 2 cases on flat background, these 2 series, we already succeed eliminate this gauge dependence. So actually, we can use this technique to obtain originally that is gauge dependent 1pi 2-point function. Then include this QG correlation from the source and observer to form the gauge independent one. Then we can use this effective field equation, because if this part is gauge independent, by including the QG correlation from source and observer, this is only gauge dependent, independent. This is for the messages in Markov scalar. And the second one is for the EM on the flat background. So this is gauge independent one. And of course, the result you obtained from this effective field equation must be gauge independent, because the only gauge dependence object is only this through this 1pi 2-point function. And right now we make a correction to this part and make it become gauge independent. Delta T here just defined this way, T minus T plan. Delta R is this norm of spatial coordinate separations. And we also solve this effective field equation perturbatively. And also we can see this is non-local, highly non-local, but if we compute it using the Schwinger-Keldysh formalism, we are going to obtain the real and the causal result. So you might say, okay, why you bother compute this on flat space, even though this thing's a step, but on flat space, the quantum gravity correction is very, very small. It's very small, but it doesn't mean it's zero. So you still can use this kind of a technique to study, for example, blurring of this light cone, etc. Okay, so this slide actually just summarizes the procedure, how to purge gauge dependence from a field's linearized effective field equation. The first step, couple the field to a massive source observer. Then the second step, scatter source and observer through exchange of the field you want to purge out the gauge. The third step, quantum gravity actually corrects this field's propagator, this original 1pi point part, and also quantum gravity corrects the vertices and also this source observer propagation. That is a diagram you can see. I show you on the previous slide. It's a 2-point, 3-point, 4-point amplitudes. And the next, you use the very important part is this part. Use the Donahue identity to extract this 2-point contribution from the 3-point and the 4-point amplitudes. And this is the other example of a Donahue identity. So this is two derivative acting on this, which is 4 propagator. 2 are massive 1, the other 2 are massive 1. We will only want to depth the massive 1 here. So use the propagator equation. Then final step is use the propagator equation, write it in the standard form, regard this 2-point contribution as correction to the field's 1pi 2-point function. So this is the procedure. We already succeed in flat space time background. Okay, so here. The really important part actually is we actually really want to apply this technique to inflation. During the inflation, actually the quantum gravity effects were significant. So you know that during the inflation, I just commented at the beginning, even asymmetries exist, it's not observable. And the procedure we already developed for the flat space type background, it seems to we can generalize it to non-trivial background. So let's review this de Sitter background here. If we write down the matrix on de Sitter in conformal coordinates, A is scale factor, eta here is conformal time. This is relation between scale factor and the conformal time. And the other object we use a lot is length function. This AA plan times h squared times delta x squared. So for the same theory, actually, we have the same diagrams and also vertices, but the vertices actually acquire some scale factor because you can see it's entered from the background matrix. And also the propagator compared with the flat space time become very, very complicated. For example, this is the massive minimum couple scalar. K is D-dependent constant. Here, you can see this scalar propagator, the final line is infinite series expansion. And you have this divergent constant, logarithm A plan is part of tail turn. This turn is flat space descent. This is also the other tail turn. So let me go back to let you to see again this massive minima couple scalar on flat space time. This is, I think, in this one. Okay, this is massive minima couple scalar propagator on flat space. Okay, so only one turn. And when you switch from this flat space to de Sitter, become very, very complicated. Okay, this one. And the graviton propagator even worse, because you know the graviton have indices and also the gauge issues. And here actually we just choose the simplest gauge, that is alpha equal to 1, beta equal to 1, and we add a similar average gauge condition to the Lagrangian density. And the F mu here have extra piece on d theta, this d theta breaking term here. So in this simplest gauge, we call simplest gauge actually have some reason. That is because it Y up this graviton propagator only have 3 pieces. There is A-type tensor times A-type scalar plus B-type tensor times B-type scalar propagator, and plus C-type tensor times C-type scalar propagators. And the advantage of we call this simplest gauge is because this tensor actually no space-time dependence. It's only formed by this eta mu nu over this delta function, delta 0 mu, etc. For example, this A-type tensor, the purely spatial, and eta bar mu nu means the spatial components of metric. And also the simplest thing for this gauge is why we call simplest gauge, is because on d equal to in d equal to 4, even though this d-dimension propagator very complicated, but d equal to 4 it becomes simpler. This A-type is d equal to 4, B and C-type in d equal to 4 dimension. So even though if you use the dimension regulation, you have to turn on the d-dependent. However, if you encounter the finite part, you can immediately set up d equal to 4 just to simplify the calculation. So if you have a d equal to 4 simple form propagator, it's advantage. So this is why we call the simplest gauge. And other gauge actually is very, very complicated. I do not show you here. And also, if we want to apply this phase space-time technique to d theta, we also want the system, simple system. And also, this system have secure effects. That's you have a significant quantum gravity effects. And the system we pick up is still the massive mean-large couple scalar. Okay, so this is effective field equation for massive scalar propagator. And we already obtained renormalized self-mass square on d theta. So the first term and the second term, you can see it multiply with this Dirac delta function, this local term, and all other term here to the end, this all non-local term, and mu here just the mass term of dimension regulation. So this compared with the phase space-time, of course, become more complicated. And the source we pick up is mimic to this point source for the point charge in the electromagnetism. So this K is constant, A is the scale factor, and this is a spatial delta function. So the tree order of this potential is not as simple as Coulomb potential. You have extra piece that is this logarithm HR times 1 over A. And at that time, it becomes simpler. So at that time means the scale factor A become very big. So you take out, you just extract out the logarithm HR. Then you have a H1 plus 1 over HAR. You spend out this small quantity 1 over AHR in the logarithm. So this 1 over AHR is leading term will cancel out this term. So only have at that time only this term survive. You also can check out the space-time limits, which is at H approaches 0, A equal to 1. We have a Coulomb potential form, similar to Coulomb potential form. So this one loop result, the full result is very complicated. However, if you only look at the leading that time, the contribution important part actually only from the first term, that is this term here. And we find out the correction, the one loop correction to this potential is this term here. It's minus kappa square H squared divided by A pi square times logarithm HR. So this is the whole potential for this source, this is tree order, and this is the one loop order. We here just rewrite the Kappa square 16 pi g. So our program is actually include Dr. Gavan and Professor Polkopets at Utrecht University and also Professor Wood at University of Florida. We want to apply this gauge purge to the mechanism in our Kappa scalar on the theta for the alpha equal to beta equal to 1 gauge. And we have the same diagrams as for the flat space-time. And we also have to make a clever guess for this simplest generalization of downhill identity. This is a very crucial step to purge this gauge dependence. And we expect the numerical coefficient of a large logarithm, that is, we obtained without this QG correlation from the source and observer. There's just a gauge dependent 1pi 2-point function. One, you get it from the effective field equation. We expect after we have quantum, after we include this QG correlation from source and observer, we expect the space-time dependence, this large logarithm still exists. This is why we our expectation, but this coefficient of course changed. And then the next step we are going to do is we are going to check for the gauge dependence. So we cannot just pick up one particular number because alpha equal to 1, beta equal to 1 is some particular number. So here we would like to do next is to check out this gauge dependence at the linear order in alpha and beta. And we already have a propagator, the graviton propagator in 2-parameter family of this theta breaking gauge. So we are able to do that. And the next, we can explore this technique for other systems, for example, the EM plus GR on the theta for the Coulomb potential and the photons. So this is the result already obtained without this QG correlation from source and observer. This is a Coulomb potential. The first term is tree order term. This is a flat space descent term, and this is pure de Sitter term. So it goes like, I think this drop out h square here, so h disappear. Times logarithm AHR. This is a photon mode function. This only have tree order and this purely de Sitter terms. Of course, finally, we would like to apply to more general case or other system, for example, quantum gravity plus fermion and purely quantum gravity interaction one. So this is final conclusion here. Makes no sense to abandon the field equation for S matrix with quantum gravity. We even know this original field equation is gauge dependent because 1pi 2-point function. But S matrix even exists in cosmology, it's not observable. We are not able to collect entirely final scattering result because this is a rapid space-time expansion. So we still try to approach in the effective field equation direction. And here, even this is non-local because 1pi 2-point function, but if you compute that the effective field equation in the context of Schwinger-Keldysh formalism, we will still get a real and causal result. And the gauge indeed a big issue, so we do need to eliminate the gauge dependence in this 1pi 2-point function. And this gauge dependence actually caused by we ignore QG correlation of the source, which disturbs effective fields and observer who measure it. So the idea is model as position space scattering amplitude. Then we get this 2-point, 3-point, 4-point amplitudes, and very crucial steps using this downhill identity to extract these 2-point amplitudes from these 3-point, 4-point amplitudes. And after we take out that one, so we use the propagate equation and rewrite it in a standard form we can compare. So we can regard the form, the expression we get as the correction to 1PI 2-point function. This already works, already succeeds. At least the two model on phase space, on a phase space time. So one is Markov scalar exchange potential. This is the ideal venue for the de Sitter generalization. And we also expect a large logarithm still exists, of course, with possibly different numerical coefficient after you make this 1PI 2-point function become gauge independent. And the other large logarithm, we also have to check that is other system like quantum gravity plus EM, electromagnetic quantum gravity plus fermions, and also purely quantum gravity, these fields will only just interact with itself. So this large logarithm could cause perturbation theory breaks down. And if, of course, we have to check because a lot of people believe this large logarithm actually is just a gauge artifact. And our program is to try to falsify or validify this is true or not. So this, I think it is a very interesting program. And if these logarithms exist, and of course you can expect this logarithm A and become very, very big at that time or at a large distance, for example, logarithm HR. So of course it could have a chance make a perturbation breaks down, even though the loop counting parameter is very small. And perhaps this kind of effects could survive even the current day. So this is my talk, and thanks very much for your attention.
Okay, thank you very much for your interesting talk. Questions, please. Raise hands, please. Okay, I see one question from Oleg Teryaev. Oleg, please ask your question.
Okay, thanks for interesting talk. And I have actually a couple of naive questions. And first question is concerning Donahue identities. Is it true that these identities implement the low energy theorems for quantum gravity, fixing the term of zero order in momentum and linear term? And is it sufficient to, does this appear sufficient to prove the gauge independence? And is it in this sense similar to QED, that this low energy theorem is more simple, fixing only term of zero momentum? This is my first question. And second question is also relation to concerning the relation to QCD and probably QED. It concerns axial gauge. The axial gauge depends on gauge fixing vector. And there is gauge independence, that the result does not depend on this vector, and it restricts the QCD result of QCD calculation. So just this is a question about analogy with gravity, QED, and maybe QCD. Thanks.
Okay, so let me try to answer your first question. I think you raised a very interesting question. I think your question is whether or not this Donahue identity still valid at high energy scales. And I will say answer is yes, because you know there's a very special part in the loop corrections that is from the loops of massless particles. This part entirely cannot be changed because you know right now our gravity theory is not complete because we just you can say it's treated as semi-classically, and we do not have a full-blown quantum gravity, so we don't know what the correct quantum gravity for the very high energy scale. And this is true. However, there's a certain part of Graviton loop contribution actually will not affect it at all at high energy. That is non-analytical part. So at this high at this that this quantum gravity is not renormalizable, and we can add this counter terms, and because this counter terms actually have a counter terms. The purpose of counter terms, of course, you want to eliminate this Bell divergence in your original calculation. However, it still consists of this finite part. So the finite part, because non-renormalizable property of quantum gravity, because right now we have not have this renormalized full-blown quantum gravity. So you might think, okay, this finite part will change this make a result very different. You could change very big. But what I want to mention that is non-analytical parts which Donahue got from his calculation, that is only contributed to long-range force part. That part actually will not be changed by the local finite part of contents. And also, even for example, there's a space alien know what is the full-blown quantum gravity. They have full control of quantum gravity. If they compute this part, they will get exactly the same piece. That part, non-analytical part, exactly the same. Okay, so I think you make a very interesting point here, and you also ask whether or not this is similar to. I think you ask the Fermi theory, right? Is this effective? You can consider Fermi theory as effective low energy theory to the standard model. The answer is yes. So this is the same. The same idea, yeah, the same one. Okay, so this is your first question. And actually, I'm not sure your second question. You mentioned this SEO gauge at QCD and also in
QD. Axial gauge, it depends on gauge fixing vector. So the four-dimensional scalar product of field to this vector is 0, and the result, and sometimes the result is needs to use the axial gauge, but it should not depend on of this gauge fixing vector. And this puts some non-trivial constraint for some equation for the result, also for non-perturbative calculation. So my question is, maybe the situation he is a bit similar, that you mentioned that it is not really the difference between gauge invariance and gauge independence. So you need to use some gauge, but the result does not depend on the specific gauge you use. So maybe somehow it's a bit similar. Actually, by the way, it's not always mentioned, but it is obvious to see that this gauge is basically the same as the gauge condition for Dirac monopole. But here it is the direction of Dirac string. So then the result does not depend. It requires the existence of string, but it does not depend on the direction of string. So maybe this such similarity. Of course, it's just very rough and naive idea, but maybe something can be just used some similarity with these problems. I see the similarity that you need to have gauge, but the result does not depend what is the specific gauge. So maybe like that.
Okay, thanks very much for your comment. Yeah. I think I will think more deeply about this question, because I'm very sorry, I'm not very familiar with this SEO gauge at QCD.
This is
But,
particular example. Yes.
Okay. Yeah, okay, thank you very much.
Thanks.
Okay. More questions, please. I don't. There is one more from Shravan. Please, Shravan, ask your question.
Hey, thanks for the very nice talk. So I'm wondering, because in all your computation, you consider minimally coupled fields, right? So but well, from in generic point of view, quantum, if we have quantum gravity, most likely matter couples to gravity may be much more complicated way. So I don't know if we change way matter couples to gravity, maybe some of these problems can be eliminated. I'm just speculating. Is it? Did you think
you
about?
mean you want to pick up the fermion system, fermion coupled to gravity? Yeah, the problem is actually matrix-linear coupled scalar is simplest problem to check first, because we're still not sure this technique will works for the non-trivial background. And you said, of course, the material is made from the fermion. So you said, why not we pick out the fermion plus the gravity of the system? The problem is we have to the scattering of this observer and the source. You have to pick up the other kind of particle, because for example, the middle line is fermion. And you have to think of what kind of interaction fermion can have. So you can pick up for this scattering observer and the source, right? So in this case, if the middle is fermion and the scattering amplitude, actually we are not able to use the scalar, massive scalar. We should use the other one, for example, like a massive fermion kind. So this is actually much more complicated the system, much more complicated system than the matrix-linear coupled scalar system. And indeed, what you comment is right. Why not use the fermion? Because our world is really made by fermion, not this scalar. We don't know why it's scalar, but in this not a really mature stage, we want to check out whether or not this technique still works on this theta. So we would like to pick up the simplest one. And indeed, the fermion case, actually, we have thought of it, but later we give up. It's because we want to check out the scalar one first. Then if this works, then we'll go for the fermion one.
Okay. Yeah. Well, I have another short question. If I didn't understand why there's no implication for inflationary correlations, because four-point correlations of inflationary perturbations. So this result should imply something, right? So for non-Gaussianities, I mean for trispectrum.
Okay, your question is more far away from the current stage. Yeah, of course, you said you want to check out all the calculation. I think so far, what people compute is still the tree order, even
Yes.
for the. Yeah, indeed, if you want to include this loop correction to the bispectrum, or even this primordial, this scalar power spectrum or the tensor power spectrum, this kind of calculation, I think that we only have. I don't think anyone have done this loop correction to it. Some people claim they did it, but if you really look at it, I think they use a lot of approximations.
Yeah, that's true.
Yeah. So indeed, this is the issue. You said, okay, in cosmology, and if we want to really compute the quantum corrections, then of course this gauge still is the issue. And indeed, this is why this is our motivation why we want to eliminate the gauge dependence. Yeah, because at the beginning the naive, the thinking is, okay, we just use the first space-time make a negus, but the first space-time we all use the S matrix as the gauge-independent object. The problem is it's not valid for cosmology, so then we have to think the other way. And I will say this is not very easy, but I think it's a very important question. Yeah.
Okay. If I may ask one more question, well, actually, I want your opinion on this, because in the previous talks, other quantum gravity approaches, especially from string theory, people prefer ADS. So do you have any comments of implications of your computation for ADS?
No, actually, I don't have a high opinion about this ADS stuff because, no too much comment on the part. And also, I probably is not the good person to comment because I have not touched, I have not followed the string theory, their work for a long time. Yeah, sorry about it.
I just want to know. Okay, it's fine. Thank you.
Do you want to ask something more? If not, let's ask other people. Any question, please? More questions, please? If not, maybe I will ask some general questions. You discussed quantum gravity plus Young plus electromagnetic field, quantum gravity plus Dirac field. And what do you expect some specific things if you study quantum gravity plus supersymmetrical generalization of Young of electromagnetic theory?
Oh, you.
I mean, just because in one of the last your line on your presentation is written quantum gravity plus electromagnetic, quantum gravity plus Dirac. So a natural question arises if you get some specific stuff, if you consider supersymmetrical generalization of electromagnetic field. What do you think?
Oh, okay. Actually, I do not consider that. It's because all the supersymmetry, because what I compute, since I try to connect with the experimental stuff, and even though my stage is still far away,
okay.
Yeah, so it's still far away, but this is my direction and approach for the supersymmetric theory. At least so far, I have heard about the supersymmetric spontaneous breaking and at the low energy, but so far, CERN or any experiment have not observed any evidence for that. So this is why, and also, the supersymmetric theory is much complicated than than this fermion theory and also Dirac theory. So let me start from this simple one first. Yeah, but maybe it's interesting to consider, but it depends on what kind of question you want to ask and why you want to couple quantum gravity to the supersymmetric theory. For example, if you want to apply this to any possible measurement, or just want to play explore the different theory for fun. I don't know. I think it really depends on your goal. Yeah.
Okay. More questions, please? I see one more question from Shravan, yes. So
okay,
this is person to person.
Okay, I asked you about ADS, but I want to just say my expectation naively based on how I understand your computation. So what people in ADS CFT claim that it is something valid at the Planck scales, or maybe it's a duality. It has to be there in a theory of quantum gravity. So of course there is this conjecture, but looking at your result, I naively expect because of this appearance of these large logarithms, this should break ADS CFT correspondence or gauge gravity duality. So I think this maybe if you apply this, it may be an example that ADS CFT doesn't work really if we take into account graviton loop corrections to the matter fields. So it may be a counterexample to ADS CFT. So this is how I'm just naively expecting.
Okay.
I don't know. Maybe wrong, but yeah.
I also don't know about it.
Okay. I don't see more questions, so let's thank the speaker again. Thank you very much for your interesting talk. Don't forget to send us your transparencies. Okay.
Okay. And
Okay.
also thanks very much for your all patience to listen. Okay. Thank you.
Okay. Thank you.
Thank you very much.
Thank you very much. Maybe just for not for public, I would like to mention, especially for you, our very old paper with Fadeev and Slavnov, where we discuss S metrics for in terms of a background field. This is before to many other people. Maybe I will send you a reference.
Okay.
Maybe it would be interesting for you. Okay.
Okay, thank you very much. Yeah, I would like to know that.
Okay, okay. Hello. So bye-bye.
Bye-bye.
Bye-bye.